Today's lecture will discuss the fundamentals of photodetectors as applied for devices such as fiber communication, for night vision, for remote sensing, etc. Now, photodetectors can be classified broadly into two categories. Depending upon their basic principle of operation. We have one class known as thermal detectors, whose basic principle is the heating effect of light on materials, and the other class are called quantum detectors, which rely on light being composed of photons, such that each photon generates electron-hole pairs or may eject electrons, which give rise to current, which is finally detected. Historically, thermal detectors were the first type to be discovered. This was in the 1820s and 30s, when it was found by Herschel that the electromagnetic spectrum was not just limited to the visible, but it extended into the infrared. And if you remember Herschel's famous experiment, that when he focused light in the infrared on thermocouple, he found that there was considerable heating effect in the region of spectrum where the eye was not very sensitive. So this was the method of detection of infrared radiation by Herschel. So thereafter, a number of thermal detectors were developed, and if I may classify them, I can classify them into thermoelectric, bolometric, and pyroelectric detectors. Thermal detectors have the advantage of having a wide spectral range, right from the UV to the millimeter wave. They do not require cooling. They are quite rugged and inexpensive. However, their limitation is that their detectivity is rather poor compared with quantum detectors. So we'll discuss thermoelectric detectors and bolometric and pyroelectric in brief, and then go on to discuss the various types of quantum detectors. Quantum detectors can be classified into various types. Depending upon the phenomena involved. Again, historically, the first quantum detectors were obviously the photoelectric detectors. If you remember, the phenomena of photoemission was explained by Einstein in 1905, and that was the first time that it was explained that light in the way of photons interacted with matter and ejected electrons from a material, from a metal, to overcome the work function. Broadly, another class depends upon photoconduction, so photoconducting. Then photovoltaic. Phenomena of photovoltaic effect was discovered as long back as 1833 by Becquerel. He found that if light was incident on a semiconductor dipped in an electrolyte, a small voltage was created, and this forms the basis of photovoltaic devices. We can also say that there are, based on modern technology, MOS or MIS type of detectors. There are photo FETs, and we can also classify phototransistors. And the most recent devices are called QUIPs, quantum well infrared photodetectors, which arrived on the scene less than 10 years back. These all have their advantages and disadvantages, and we'll compare these advantages and disadvantages. But comparing quantum detectors with thermal detectors, it can be said that, broadly speaking, quantum detectors have limited spectral range. They have high responsivity over this limited spectral range. Many of these devices should be operated at low temperature for high sensitivity. So they gain in detectivity by operation at lower temperature. Some of them can be operated down to about 4 degrees K, but more typically 77 or 100 degrees K. They're much more expensive. Most of them depend upon modern semiconductor technology for their fabrication. And of course, they are devices which are often limited by noise, and so as a result, one gains by operating at low temperatures. So, quantum detectors and thermal detectors occupy separate niches, and depending upon the applications, one uses either quantum or thermal detectors. Now, when we are talking about detectors, right at the outset, we should discuss that how are detectors specified. What is it that we want from detectors, and how can we compare one set of detectors with another set of detectors? Now, these being photodetectors, we are interested in detection of electromagnetic radiation. As you know, electromagnetic radiation spans a huge wavelength region. In this, we have to obviously, for photodetectors, we obviously have to specify what is the spectral range and the width. Do we want a wide range or do we want a narrow range given a particular spectral width? For example, in the case of night vision, we want to detect between 8 to 12 microns. For fiber optic communication, we want to detect radiation only at 1.3 or 1.5 microns. We want to reject other wavelengths so that the noise is reduced. Spectral range, typically we can, there are detectors that go right from UV to microwave or millimeter wave, but we shall mainly consider from the UV, say 300 nanometers, to a wavelength in the IR of, say, of the order of about 20 microns. wavelength. So this is one prime consideration in the choice of detectors. Then what is the intensity distribution of the source that we want to study in terms of either watts per hertz per centimeter squared, or in case of quantum detectors, photons per centimeter squared per second. Now, for specific applications, we are interested in what is the spatial or angular distribution. Do we want to detect light from a wide object covering a large scene, as in the case of night vision, or do we want a very specific narrow area source like an optical fiber? Then, considering the nature of the sources, the temporal variation is important. With how does the light source vary in intensity with time? Is it slow or is it fast? If it's very fast, then it requires a fast detector. So temporal variation of both intensity, and in some cases the spectrum itself may vary. So this is important. So these are sort of source specifications, okay, for which the detectors must be suitably chosen so as to provide the requisite information. If we have a laser as a source, then the phase information may be required for a coherent source. Especially if you have several sources, we may want to study the phase relation between them. And of course, inevitably there is noise. The intensity and spectral distribution, the variation with time is important, because noise forms the lower limit of detectivity, which limits the operation of detectors. So, if we want to have photodetectors for these specific types of sources, then we have to classify the detectors and in comparing detectors we have to specify the parameters of detectors. One of the important parameters is responsivity, given by R, which is defined as ratio of the RMS component it's the RMS value of the fundamental component of the detected signal to the RMS value of the fundamental component of the incident radiation power. We say fundamental component because in general we may have a signal which varies with time. The signal amplitude may vary with time, and if we fully analyze such a signal, then obviously we will get some fundamental components superimposed on which there are Fourier components. So this is the fundamental component, and we want to, this is the peak value, we want to find out what is the RMS value of the fundamental component and compare with the RMS value of the fundamental of the incident radiation power, which is causing this signal. So R responsivity can be given by V of J into A. This is in volts per watt, where V is the RMS signal voltage, J is the incident radiation power, and A is the area of the detector. Notice that this responsivity will be wavelength dependent, and so we often write R as R lambda. And so this responsivity is so many volts per watt. And the higher the responsivity, obviously, the more sensitive is the detector. Here, notice that the area is coming in into the denominator. Another very important parameter for comparing detectors is the detectivity, and this is typically what is used for comparing, say, thermal detectors and quantum detectors. Detectivity is defined as the signal to noise ratio produced with unit radiant flux incident on the detector. So this is often a figure of merit. The higher the detectivity, the more sensitive the detector. And detectivity D star, which is a function of the bandwidth, the frequency of operation, and the wavelength of the detector, is defined as A to the power half. A is the area, delta F is the bandwidth to the power half, over Pn, where Pn is the noise equivalent power. Or NEP for brief. The unit of this is obviously centimeter hertz to the power half by watt. Centimeter from here, hertz to the power half over watt.
What is
F is the frequency of modulation of the signal. The question was, what is F? F is the frequency of modulation of the signal. That means, suppose you have a signal working at, say, 1 micron. Okay, that 1 micron signal may be modulated at 100 megahertz. Okay, and delta F at 100 megahertz, what is the bandwidth of that signal? Okay, at 100 megahertz, the bandwidth may be, say, 1 megahertz. Okay, so this is that bandwidth, delta F. A is the area. A is the area in centimeters. Okay, centimeters squared. Okay, so that's why this is centimeters. Delta F. Let me write. This is the bandwidth. At frequency, at modulation frequency F. Okay. Okay, sorry. B is here. It's B in this case this is called bias. Okay, this is B. This is a bias across, say a p-n junction or a photoconductor. B stands for bias. F is the frequency. And lambda is the wavelength. This is the wavelength of the source, and frequency is the frequency at which that wavelength is modulated. Okay. Okay. The most important term, most of these terms are obvious, but Pn is not so obvious. Pn is the noise equivalent power. And what is Pn? Pn is equal to, is the minimum radiant flux required to produce unity, to produce signal to noise ratio of equal to unity. Okay, so this is noise equivalent power. There is a certain amount of noise. Pn is the signal which is required to produce, which is the radiant flux which is required to produce a signal to noise ratio of 1. So you see that if the noise is low, then Pn will be low and the detectivity will be high. Okay, so apart from these constants, okay, these parameters, D star is inversely proportional to NEP or Pn. Okay, the noise equivalent power is small, then the detectivity is very high. And obviously you can write that Pn is equal to, okay, this by D double star. Okay, so this D star is one of the most important figures of merit, and we can say that, just broadly speaking, say for cadmium sulfide detectors at lambda about 0.5 micron, detectivity can be as high as 3 × 10⁻14 centimeter hertz to the power half per watt at 300 K, and for MCT, for example, D star at lambda at about 10 microns, near 100K. D star can be something like 2 to 4 into 10 to the power 10 centimeter hertz to the power half by watt.
Material dependent, not device dependent.
Question was, is this material dependent or device dependent? It is both material dependent and device dependent. Okay, and it's also wavelength dependent. Okay, like I've put here. Okay, it depends upon the wavelength. Okay, it depends upon the modulation frequency. It depends upon the bias, and it's obviously a function of temperature, because in the semiconductor, as temperature increases, carrier concentration increases. Okay, generation, recombination, noise increases as a function of temperature. Okay, so it's very strongly a function of temperature also. For example, if you have a polycrystalline material, it is material dependent. I'll give you an example. For example, if you have a polycrystalline material, you have grain boundaries, then you have conduction between grains that can give rise to noise. If you have single crystal material, no grain boundaries, there is no noise due to carrier fluctuations. Okay. Device dependent, okay, whether there's a junction or whether there is no junction. Okay. If it's a photoconductor, there's no junction, so there is no shot noise. If it's a photovoltaic device or a Schottky barrier with p-n junction, then there's shot noise. Okay, so different components. If you have this B bias, I included this in the last moment. APD. Okay, APD is a device that works at high bias. Okay, so at high bias, impact ionization occurs. So this is an additional source of noise. Okay, so the noise, this will go up, and then detectivity will come down. Okay. So all these parameters are important for determining the figure of merit, the detectivity. And broadly speaking, quantum detectors have lower detectivities, typically of the order of for thermal detectors. The best thermal detectors have detectivities of the order of well, generally speaking, detectivities would be of the order of about 10 to the power 8 to 10 to the power 9, compared with 10 to the power 10 for quantum detectors. Okay, let me continue and define the other terms. Of course, the frequency bandwidth is another very important property, especially if you're in the field of communication, when the data rate is very high. What is the frequency bandwidth? This is the modulation frequency. At which response decreases by 3 dB from its maximum value. And if tau is the response time, then the frequency bandwidth is given by the spectral response is also an important parameter. For example, if you're suppose this is the maximum response, one can say that this detector has and say this is down by 3 dB. So one can say that this is the range over which this is the range of wavelength over which the detector has a response which is 3 dB below the maximum value. Okay. So this is especially important for quantum detectors which have limited range. Typically in a quantum detector, one of the limits will be the band gap, or some donor or acceptor levels. For energies below that, for example, typically you take a, so if this is Eg, okay, so H nu must be greater than or equal to band gap, and so at the long wavelength region, okay, so this is equal to Hc by lambda, okay, so there will be a long wavelength cutoff 1.24 by. So this is one of the factors that determines the spectral range. The responsivity is the overall external response, but as far as the internal efficiency is concerned, we have a term called the internal quantum efficiency of a detector. It is at an internal is the number of carriers generated to the number of photons incident. In the case of quantum detectors, this can be approaching almost 1. However, there is an external quantum efficiency which is the ratio of the number of carriers collected at the electrode over the number of photons incident. And this is eta x is less than eta internal because there may be collection losses, and for example in a photoconductor, if carriers recombine before collection, then obviously the number of carriers collected is going to be less than the number of carriers generated. Okay. So from the device point of view, finally it is the external collection efficiency which is going to determine the responsivity. For certain types of detectors, gain is also an important parameter. Gain is the number of carriers crossing between electrodes to the number of and you would think that this gain for many detectors would tend at best to 1, say for photovoltaic detectors. But in many cases, G can be greater than 1. Obviously, if you have high field phenomena like impact ionization, followed by avalanche multiplication. So for avalanche photodiodes, we can have gain which is greater than 1. That means one photon gives rise to an electron-hole pair. Then that electron, due to high field, can create additional electrons, so that finally we have, for one photon, many more than 1 electrons and holes collected. So that is one case. And also for photoconductive detectors, we can have gain greater than 1, as we'll see, if the lifetime gain is then given by lifetime over transit time, okay, and if this is greater than 1, then we can also get gain in a photoconducting detector. So, broadly speaking, I've just covered what are the properties of the sources and what are the general parameters of photodetectors, which can lead you to compare between detectors and give you a means of choosing between which detector is suitable for your particular application. Now, since we are talking about detection of electromagnetic radiation, we should be aware of what is the background radiation which is present, and we know that according to the Planck distribution, at a given temperature, the intensity of radiation available is given by, say, at 290 K, the background emission, say it's called theta lambda, is a maximum at around 10 micron, going from, say, 1 micron to, say, 1,000 microns. This is a consequence of, this is Planck black-body distribution relation. So, if this is the overall radiation density which is available, then the detectors working in this environment will have a detectivity which is inversely related to this. So, since the noise is going to be, background noise is obviously going to be highest at this wavelength. So, how is the detectivity of detectors, black-body limited detectors, going to vary? The ideal photodetector, if I draw it on the same scale, the detectivities will be inversely proportional will just be so this will be the so this is the limit of detectivity of quantum detectors. We cannot exceed, even for an ideal detector, the detectivity given by this graph. That's why when you plot the detectivities of available detectors, one always has a plot of this type, and it has the ideal detectivities this is D star at 300K. Okay. So where and at 77K the detectivities are obviously going to be there's obviously a shift in this wavelength minimum, and there's an increase. So all available detectors will be plotted on this graph. For example, a germanium detector will occupy detectivity curve around that region. Indium and tibonide detectors will be there. At low temperature, one can have detectivities of there. The cadmium sulfide one that I mentioned, that this is say 0.1, this is 1 micron. Cadmium sulfide detector occupies a position here, whereas the mercury cadmium telluride detector occupies at 10 micron. This is say 10 to the power 15. This is 10 to the power 9 in the appropriate units. The mercury cadmium telluride, this is 10 to the power 14. Mercury cadmium telluride detector at about 10 microns will have a niche around there. So in this talk, what I've done is reviewed what are the different types of detectors, thermal versus quantum detectors, and I've discussed what are the characteristics of sources, and finally what are the important parameters of detectors.